Okay, so we're going to prove the double angle formulas for both sine and cosine. So the directions say the following identities are known as double angle identities, but they are just special cases of the sum identities that you just found in previous problems. Now prove it. So the first formula that I'm going to use, the first identity I'm going to use is the alpha plus beta. So I'll write that over here. It's sine of alpha plus beta is equal to sine, cosine, cosine, sine. That's not how you spell sine. So sine, cosine, cosine, sine. And sine matches. So if that's a plus, if this is a plus right here, then this is a plus right here. So they match. Okay. And then I'm just going to go through with alpha and then beta. Those are just Greek letters. Just think about them as X and Y. But in the land of trig, we tend to use Greek letters because the other letters actually mean something in math, right? So I'm going to use this identity to rewrite this identity, sine of alpha plus alpha. So the first thing that I'm going to do is I'm going to go sine, cosine, cosine, sine, just like I did before. Oh no, you're running into each other. That's okay. And then it's a plus because it matches. And then you just write alpha all the way through because it's all alpha. Everybody okay with that? And then you say, okay, wait, sine alpha cosine alpha plus cosine alpha sine alpha. Anybody notice anything? Does anybody notice anything? Okay, I missed someone's. Yeah. So this is literally what's an orange plus an orange. Does everybody see this as an orange plus an orange? Does everybody see those as like terms? Some of you are like, no, because sine alpha, cosine alpha came first in the second one. They're the same thing because 4 times 3 is the same as 3 times 4. You can commute those, right? That's what it's called, commuting them, switching places. So what's an orange plus an orange? No, 2 oranges. Yes. Okay. So we get 2 sine alpha cosine alpha. So when just like let that sink in for just a second. Sine cosine plus cosine sine. Hey, Miss Johnson, how come it didn't work for the other side? How come it didn't work for the identity that you initially wrote down for us? This one up here. How come it didn't work for that one? Because your alpha and beta were different. Your alpha and beta were different. So 2 sine cosine is your double angle formula. So now you can use this thing. You could have used it before, but I'm just going to write it down. So sine 2 alpha equals 2 sine cosine alpha. Okay, so this is another formula that you now can use. It's a tool. You could have actually used it before, but now you know where it comes from. Like, so what they're trying to make sure you understand here is these identities that are on our trig sheet here, and this is just one trig sheet. I literally Googled trig sheet and this is what I got. Okay. So what I'm trying to tell you here is these aren't random. These are actually built off of each other and the definition of sine, cosine, tangent, right? So these aren't random. So if you wanted me to, hey, Ms. Johnson, can you prove to us the sum to product identity? Can you prove it to us? Sine alpha plus sine beta equals 2 sine alpha plus beta divided by 2. Can you prove that to us? Yes, I can. But for our purposes, now that you have access to this whole trig sheet, I highlighted the ones. Actually, now we need to highlight these ones. I highlighted the ones that we went over so that when you guys are taking a test, you know which ones you should be very familiar with. Does that make sense? It's not to say the ones that are not highlighted are not going to be used. It's just to say these are the ones that are really useful. Okay. All right. Back to work. Okay, so there's that one. And then cosine alpha plus alpha. The trig identity of cosine of alpha plus beta is cosine cosine sine sine, where cosine does not match. So if it's plus on the inside, it's minus on the outside. Okay, and then you just go in here and you write alpha and beta. Alpha, beta. So how I write this down is exactly how I use it. I literally write cosine, cosine, sine, sine. Wait, it's cosine, so it's minus alpha, alpha, beta, beta. If those are numbers, I'm not writing alpha, I'm writing the number. So this is how I use it because, I don't know, it's just useful to me like this. Okay, so they want us to prove this. So I'm going to use this identity in order to prove this one. So cosine alpha plus alpha, it's going to go cosine, cosine, sine, sine, right? With a minus. But now this time it's all alpha, 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 alpha. Everybody good? Now up here we had orange plus orange equals 2 oranges. Everybody see that? Do we have that in this case? Everyone says no. Cosine, cosine, sine, sine are not the same, right? These are not 2 oranges. Does anybody see anything that we could do? Does anybody see anything that we could do? Yeah, you can simplify. So cosine times cosine is cosine squared. Does everybody agree with me on that? Minus sine squared. And some of you are like, Miss Johnson, this looks like the Pythagorean identity. Okay. Yes, it looks like it. Is it the Pythagorean identity? Is it the Pythagorean identity? So some of you are switching over to your Pythagorean identity and you're looking at your Pythagorean identity and you're telling me yes or no. Is this the same as the Pythagorean identity? So someone give me an answer in the chat. You are correct. Thank you for participating. Get this up here. Wait, this is not my... Jeez, Miss Johnson. Yeah, the answer is no. Now, for those of you who are like, but it looks the same. If it's not exactly the same in math, we can't say it's the same. Okay? Because if that's true, then I can go to the store and they could be like, oh yeah, you owe us $10. And I'll be like, look, here's $1. And then they'd be like, yeah, that's not $10. I'm like, yeah, but it looks almost the same. And they'll be like, no. Okay, so it has to look exactly the same. So for those of you who don't know your Pythagorean identity, here it is. If you don't know it, that's good. At this stage, I don't think I knew it. So sine squared plus cosine squared equals to 1. That is an identity that we have used. So some of you are looking at this and being like, man, Miss Johnson, it kind of looks the same. No, it's not the same. Okay, it's not the same. This reminds me of like when, I don't know, girls, we do this all the time. Oh my gosh, I love your shirt. I have the same exact one, except it's not red, it's blue. And it doesn't say that, it says this. I'm like, it's not the same exact shirt. Okay, so it needs to be the same exact shirt. So the fact that this says cosine squared minus sine squared, and this one says sine squared plus cosine squared, not the same. So actually cosine, the double angle of cosine has several different versions of it. This is one of them. I like this one because when I say like, oh my God, when I say this, oh my gosh, it's like the Pythagorean identity. And I realize, wait, it's not. Oh, wait. Then my next step is, is this the double angle for cosine? Does that make sense? Okay. So this is one version of it. So I'm going to put some highlight on this because we proved it. Oh no, you cannot see my alpha. Let's bring alpha back. Okay. So that's one version of it. And I'm actually going to use the Pythagorean identity to find the other ones. So another one is if you look at just cosine squared, could you solve this one for cosine squared? Can you manipulate that equation, that identity, so cosine squared is by himself. So go ahead and do that for me real quick. So this is very algebra for me. Algebra is, I have something and I don't want it the way it is. Can I mathematically rearrange it so it looks like the way I want? So this is like Play-Doh to me. Can I get the Play-Doh ball to look like, I don't know, a Play-Doh person? You probably can. I can't. I'm not very good at Play-Doh. Okay. So you should have subtracted sine squared for both sides. So I could write this as cosine squared theta equals to 1 minus sine squared theta. So Ms. Johnson, would you still call this the Pythagorean identity? Technically, yes, but not really, right? Because it's a rearranged form of it. So I don't call it anything. I just say I'm going to use the Pythagorean identity to rewrite this. So now I'm going to substitute. I'm going to take all of this and replace cosine squared with it. Is everybody okay with that? So I'm going to take all of that. I'm going to, instead of writing this here, I'm going to write this here. Does everybody see that? And it's legal because you guys have been substituting since I don't even know how long. So I'm going to write 1 minus sine squared there. So this is 1 minus sine squared alpha. And then I'm just going to copy the rest. Minus sine squared. I can't write. This is challenging today. Alpha. What's 1 minus sine squared minus sine squared? Does anybody see anything you could do? Anybody see anything you could do? Some of you are like, yeah, Miss Johnson, look, these two, this is an orange minus an orange. Yeah. So it's minus 2 oranges, right? So it's 1 minus 2 sine squared alpha. And this is another version of it. Okay. So cosine 2 alpha could either equal to cosine squared alpha minus sine squared alpha, or it could equal to 1 minus sine squared alpha. Ms. Johnson, which one would you use? I use a lot. I use these quite a bit. I usually use these when I'm either trying to go from cosine 2 alpha to cosine something alpha. Not 2 alpha, just alpha, right? That's the advantage of this one. The advantage of this one is I don't want a double angle. I just want an angle. That's the advantage. What's the advantage of this one, Ms. Johnson? This is I don't want a double angle. I want a single angle, and I don't want cosine. I only want sine. Do you see the advantage of that? This is like, which one do you want? Do you want a number 1 from in and out or number 2? Well, I like cheese. So obviously I'm going to get a number 2, right? So I want I'm trying to manipulate an equation so it just has sine in it. So obviously I'm going to use the yellow one. Similarly, going back up to the pink, back up here, similarly, instead of solving for cosine squared in your Pythagorean identity, you could have solved for sine squared, right? You could have solved for sine squared. So if you were to solve for sine squared, you would have gotten sine squared theta equals to 1 minus cosine squared theta. And then you would substitute 1 minus sine squared into here, cosine squared. I said that wrong. You would substitute. So go ahead and try that really quick. Try your hand at that, and then that is pretty much it. So I'll be right. Go ahead and try that. All right. So I'm just going to substitute 1 minus this stuff here, 1 minus cosine squared in for sine squared. Do not fall in the trap of not using parentheses, especially for this one, because then it'll be wrong. Okay. So I'm going to write cosine squared alpha minus big parentheses. And then in there, I'm going to plop all this stuff, right? So 1 minus cosine squared alpha. Now, do you see the reason why you have to use parentheses? Because otherwise, you're not going to distribute that negative, and then it's going to be wrong. Okay, so distributing the negative, I would have gotten cosine squared alpha minus 1 plus cosine squared alpha. Okay. So then my answer is cosine squared alpha minus 1. Wait, what am I doing? 2 cosine squared alpha minus 1. I think some of you got it flip-flopped. So check your signs on that. So 2 cosine squared alpha minus 1. Okay, so this is your last identity. So you could use any one of these, and you will get better at choosing which one you should use when, based on what you need. Does that make sense? What you need. So if I wanted everything in terms of cosine and not a double angle, then I'm going for the blue one. If I wanted things in terms of sine but not a double angle, then I'm going for the yellow one. If I wanted cosine and sine, I'm okay with both of them being in there, then I'm going for pink. Okay. So again, now technically in mathematics, now that you proved it, now you can use it. Okay, for all purposes, in math, you can't technically use a theorem until you've proved it yourself, or not proved it yourself, but saw the proof of it. So we just proved those identities, and so now you're able to use them. And now you understand that they don't pull them and pluck them from the sky and be like, oh, this would be a really cool identity to have. It's actually based on something. All right, thanks for listening.